Hello everyone, I am Alex from ETH Zurich and I will talk to you about NumPy-Bench, a benchmarking suite for high-performance NumPy. Python has a rich ecosystem that consists of a large assortment of modules, a potent arsenal in the hands of domain scientists. For example, SciPy provides the essential support for scientific computing. Pandas and NetworkX can be used for data and graph analytics respectively. SymPy facilitates symbolic computation. Visualizations can be created with Matplotlib and Seaborn, while IPython and Jupyter enhance productivity. This powerful toolkit drives the development of applications across a wide range of scientific domains, from molecular dynamics and climate to machine learning. However, the cornerstone of all this development is no other than the NumPy module. NumPy is ND-array, an efficient multidimensional array object. Apart from the data buffer, ND-array object encapsulate other important information such as the data type, the shape of the array, and the access rights. Element-wise array operations, for example those that represent matrix addition, are lifted to array operations that follow typical mathematical notation. Broadcasting allows operations among ND arrays of different shapes, making the Python code more concise and increasing the productivity of scientists. Furthermore, many common linear algebra operations, such as matrix multiplication, are directly mapped to BLAS and LAPAL calls for increased performance. However, this is often not enough, as the performance benefits degrade in larger and more general codes, while there are pitfalls that are challenging to work around. For example, element-wise ND-array accesses, especially inside for loops, are typically slow to execute through the CPython interpreter. Overall, we end up with a mix of general Python and NumPy-specific code that is very productive to write. However, we also want to find out how we can take this code and execute it fast. And here we have an increasing number of different options. We can start with executing our code through the reference CPython interpreter. We can use an alternative interpreter, for example PyPy. Another option will be to rewrite our code and enhance it with syntax from the Python language and compile it with a tool of the same name. Last but not least, we can choose one of many frameworks that do just-in-time or ahead-of-time compilation of Python and NumPy codes, some of which we are going to discuss also later. Now, the real question is, what is the best tool for our use case? How can we evaluate all these different options? And to answer this question, we made a benchmark, NumPy-Bench, a collection of microkernels and micro-benchmarks across a wide range of scientific domains, together with the necessary infrastructure to measure productivity and performance of different solutions for accelerating Python and NumPy codes. NumPy-Bench includes currently a total of 52 microkernels and micro-benchmarks. Allow me to shortly introduce the main scientific domains. Chemistry, with micro apps from PyPy, a Python library for azimuthal integration, digital signal processing, sparse and graph algorithms, weather and climate, with micro apps from grid tools for Python, machine learning, with implementations of 3-layer multi-layer perceptron, LeNet 5 and residual block of ResNet 50. In physics, we have Navier-Stokes equations from CFD Python, as well as micro-benchmarks from the Omen quantum transport simulator. And finally, we have linear algebra kernels and solvers from Polybench. In NumPy-Bench, we use a wide variety of NumPy syntax and features. The reason for this is that domain scientists use such features to increase their productivity, and therefore we want to test Python frameworks for their compatibility with NumPythonic codes. Let me bring you a few examples, starting from simple ones. Clipping is a microkernel that we adapted from Python's tutorial for NumPy, and here we are testing for simple array operations, array scalar operations that use broadcasting, and the clip NumPy method. Another example is this function that implements batch normalization. This is used in some of the micro benchmarks related to machine learning. And we are testing for NumPy reduction support and specifically common keywords. For example, the axis keyword, which tells which axes are we going to reduce, and the keep dims, which says whether we are going to remove the reduced dimensions or we are going to keep them with size 1. An important aspect of NumPy syntax is indexing. How exactly do we access data of NumPy arrays? We start with simple indexing, where we can slice an array with a triple start-stop step, where any of these parameters can be missing or even be a negative number. There are also specialized keywords, for example, new axis, which adds a dimension of size 1 to an array, and when combined with broadcasting, it can assist in implementing complicated operations in a single statement. Finally, we have advanced indexing, where we use Boolean or integer arrays to index into another array. NumPy includes many submodules that implement a variety of routines. For example, there is the linear algebra submodule with many useful methods for matrix inversion, solving linear system, and others. We also test for some of those. For NumPy-bench, we adapted Polybench, a popular benchmark for polyhedral compilers, to Python and NumPy. I would like to provide you an intuition of the rules that we use to do so. I will use as an example the Cholesky solver, and we start from the original C code, and we rewrite this in Python using the exact same language constructs, the for loops and the per element axis and operations. Now we take this original code and we have a look whether any of the explicit for loops can be lifted to array operations. And we can see here that there are actually some of the inner loops over the k variable that can be rewritten as dot products. Now, NumPy also includes a built-in Cholesky method that we can use, and after adapting the code to return the exact same result as the original C code, we end up with a second version for the Cholesky kernel that looks like this. NumPy-bench includes infrastructure for recording performance and providing productivity metrics. To showcase this functionality, we selected some frameworks that accelerate Python and NumPy codes and put them to the test. Before proceeding to the evaluation section, I would like to present them to you shortly. We start with Python, which is a static compiler for a subset of the Python language, including support for NumPy arrays and routines. To optimize the method with Python, we can optionally annotate the data types of the method's arguments. Python will then convert the method to an intermediate representation that is based on Python ASTs and apply on this IR an assortment of optimizations, for example, constant folding, for loop unrolling, forward substitution, and others. Finally, Python will output templated C++ code that we can convert to a shared library file by compiling it with our favorite C compiler. Next is Numba, a Python just-in-time compiler based on LLVM. To optimize the Python method with Numba, we have to annotate it with the Numba just-in-time decorator. This decorator has two main modes of operation: the object mode, which offers maximum compatibility with Python and NumPy, and the no Python mode that results in the best performance. The decorator has other arguments. For example, it can enable auto-parallelization. After Numba parses a Python method, it creates its internal Numba-IR representation, in which it applies a number of optimizations, for example, loop parallelization, loop fusion, array analysis, and copy propagation. Finally, Numba outputs LLVM IR, which is then compiled just in time and executed. CuPy is an implementation of NumPy and the array for CUDA. CuPy's API is highly compatible with NumPy. Apart from the need to use some utility methods to copy our data from the host to the device and back, most of the time we do not need to change our Python programs. It is simply enough to swap the import statement for NumPy with one for the CuPy module. CuPy is written in Python. When we execute our Python program, the calls to NumPy routines or the array operations resolve to on-the-fly creation of specialized kernels or direct calls to optimized libraries from the CUDA toolkit, for example, cuBLAS and cuSolver. The last framework that we tested is Days. To optimize a Python method with Days, we have to annotate it with the Days program decorator. Days can do just-in-time or ahead-of-time compilation. To enable the latter, we also have to annotate the data types of the Python method's arguments. Furthermore, the sizes of the arguments can be symbolic. After parsing a Python method, Days converts it to its data flow-based intermediate representation called the STFG. In this IR, it applies graph transformations to optimize the program, for example, loop parallelization and tiling, subtract fusion, and local storage. Afterwards, Days uses suitable backends to generate code for different architectures. In this work, we focus on CPU and GPU execution. They support CPUs with C++ code, while for NVIDIA GPUs, it outputs C++ and CUDA. It is time to proceed with the evaluation, and we are going to start with productivity. To run NumPyBench with the frameworks, we had to adapt the code to some degree. As we just saw, some frameworks need some extra lines, for example, to add a decorator or to type annotate the arguments. Other frameworks have some incompatibility with NumPy. They don't support some of the built-in routines, and we had to design around this by providing some other equivalent code. Let us see some examples. This is the Floyd-Warshall micro benchmark, where we make a call to NumPy add outer. So this is computing the outer product using the addition operation instead of multiplication. And this is actually unsupported by Numba. So in our adaptation for Numba, we rewrite this in an explicit for loop. Another example is this micro benchmark, the Azimussian integration that uses histograms. So histograms are actually supported by Numba. However, the weight keywords it's not. So for the second call to NumPy histogram, we had to write a new method. So actually we find a suitable candidate from NumPy tutorials and we use that one. To measure productivity, we provide two different metrics that are based on counting the lines of the programs with slot count. If we go back to the example of Floyd-Warshall, the original Python NumPy code is 4 lines long. The adapted code for Numba is 7 lines long. So the first metric is the absolute difference in total number of lines. So in the case of Numba, this is plus 3 lines. Now if we compare the two codes, we can see that to adapt Floyd-Warshall for Numba, we had to change 1 line from the reference code, the one that concerns add outer. Now, if we compute this as a percentage of the total number of lines in the reference code, this is 25%, and this is the second metric. We summarize the results of our productivity analysis in those graphs. The columns annotated with NumPy are the reference code lines, while if we look at every other cell, we will see that there is a number that indicates the absolute difference in number of lines between the adaptation and the reference code, while the color of the cell, which changes from green to red, indicates the percentage of reference code that had to be adapted. Now, overall, we can see that CuPy and Python have the highest compatibility. Numba is also very good. Days has some issues, mostly because there is a need for increased number of lines for the type annotations and the symbolic sizes, but also because it is missing implementations from some of the built-in NumPy routines. We measured performance on a machine with 2 Intel Xeon CPUs for a total of 32 cores. This machine also has an NVIDIA V100 GPU. For frameworks that have some kind of optimization flags or automatic presets, we did the following. For Python, we used the compilation flags suggested by the developers. For Numba, we created up to 6 different presets for each benchmark, changing the arguments of the Numba just-in-time decorator. So, for example, we tested with object no Python mode, we enabled or disabled automatic parallelization, and finally, we created versions of the benchmarks where we annotated explicitly parallel for loops. For this, we also created some automatic transformation presets, one preset that does what they call strict transformations, one that does loop fusion, another for fusion and loop parallelization, and finally, another one that uses heuristic to auto-optimize the code. For Python and Days that both of them generate C++ code, we use GCC 10.2. We summarize the performance results in the following figures. In the columns annotated as NumPy, we have again the reference execution through the CPython interpreter and the absolute runtimes. In the other cells, we have an arrow and a number. The arrow indicates whether the framework in this particular benchmark is slower or faster than the reference execution, while the number is how many times slower or faster. We also provide aggregations using as a metric the geometric mean. We have a total aggregation and separate aggregations for each scientific domain. We note that in benchmarks that can make use of BLAS and LAPACK, for example, the benchmarks 2mm and 3mm, the frameworks have consistent performance. This is because all of them, including the reference execution, make use of MKL and cuBLAS. Overall, we can see that Days has the best performance on the CPU with a geometric mean of speedups over NumPy approximately equal to 10. On the GPU, Days appears to be faster than CuPy, however, a lot of the benchmarks do not run due to compilation and runtime errors. Another thing to note is that CuPy has a lot of slowdowns against the reference execution because it does not automatically fuse kernels and therefore has great overheads. To close, I presented to you NumPyBench, a benchmark suite for high-performance NumPy. A collection of benchmarks across a wide range of scientific domains, together with the necessary infrastructure to measure productivity and performance of frameworks that optimize Python and NumPy codes. You can find NumPyBench on GitHub. We hope that the project will resonate with the high-performance community, and we are eager to discuss with you your suggestions for future developments.